Hi, welcome. My name is Edward Turner, and today I'm going to be talking about the empirical study of transfer learning in NLP. So let's get to it. So, the agenda today is just going to be a brief introduction of really what transfer learning is and how we can use it in NLP task. The design of the experiment that I use, along with the origins of the data. Uh, then we also have data mining, which I dive a little bit more into those origins. Then we're going to discuss some ML techniques. Then we're going to discuss some ML model architectures that I use. And then we're going to compare some results and then finish off with a decent conclusion and some references. So, what is transfer learning? Well, I took this little blob of text right here from the TensorFlow website because I felt like this is actually very, very close to how I would describe it. But transfer learning is essentially feature extraction. You're using the representation of information learned or the feature space learned from a previous deep learning network that was trained on some data. And then you're going to use that feature map to map the data that you have to that feature space. And then you use that new feature space just purely for training purposes on top of your new information. And so essentially, you can kind of think of this as almost free lunch in a sense. Now, the design of the experiment is kind of broken down into two, major fashions here. One, we're going to have a tenfold cross-validation, training process, and what this actually entails is randomly sampling data based off of a stratified split, and then training a model on, say, one randomly sampled, say, set of information, and then predicting on the untrained, the data that wasn't seen by the model. And then those inferences that I then produce are compared to the actual inferences, the actual data that you have, the actual labels that you have, just to make sure things make sense. And then you compare using whatever metrics you decide. And I'll describe the metrics I use once we get down towards the ML, architecture and also the comparison of results. Now, we're also going to do a stratified train test split. And so this purpose is actually just to make sure that we have the same training data and validation data across all the different architectures that we're going to experiment and use. And then we're going to really, again, just train on the training data and then predict on the validation data and then compare those inferences there to the actual labels that we have. And in this particular case, we're not going to measure anything from a qualitative or quantitative standpoint. We're really just going to do some comparisons in how the data is properly predicted. And that can be in form of some type of plot. So we're going to discuss that and look at those results. And that's going to be the comparisons of results. All right, so now the fun part, the data. All right, so we're using the median articles data set. And this is actually found off of a Kaggle.com more or less data set webpage that I found. And so the link is there. If you want to check it out, please go ahead. This is going to be a reference towards that. Give all credit to people who have spent the time to scrape the data from median and to represent it. Now, the goal here is to see if the content of the articles can be informative into whether an article receives high praise. So if you're not familiar with Median at all, Median essentially is a blogging website, and people who do well, who have a lot of, say, views or reads, normally have a lot of claps, which are a form of likes, if you're familiar with social media. And so what we're going to do is just see really how many likes or claps does an article receive, or can we predict that based off the content of the article? All right, so we're going to have a couple different things from a data mining standpoint that we need to consider. First is a feature engineering, which is transforming the variable class into a numeric variable. And that's because the data initially had it in a form where claps was either 900 or 39K. And 39K translating to 39,000. And so we have to do a little math here just to make sure that the actual variable that we want to predict actually translates into something numeric that we can work with. And then we're going to plot the distributions just so we can see how the data looks like overall. So this is a plot, and as you can see, the variation is pretty large. It goes from 0 to more than 50,000, approximately around 53,000. One thing to note here is the distribution. So note that it's lopsided, right? All the data is shifted towards the left rather than towards the right. And when I mean towards the left, I mean towards 0, all depending on how you're seeing the chart and how I'm actually seeing the chart. But the data is centered towards more so by 0, maybe somewhere between 0 and maybe 1,000, somewhere there. Now, for those who aren't familiar with non-zero data, typically that type of information follows what's called a log transformation or log distribution or a Poisson distribution, one of those two. But essentially, those two distributions really follow a log likelihood type, type average, across the entire distribution. And this is actually extremely helpful and useful to understand that, because then this allows us to see whether perhaps we can change the distribution of the information based off of the log transformation, which I was able to do that. We're not going to show that right now, but this is an exercise for you to try that out. Transform your data, right, using the log+1 transformation. You can use the NumPy package if you want. Or you can use a quantile transformer or power transformer available in sklearn. But try that out and see what this looks like to you. But in this particular case, what we're going to do is we're actually going to divide our data up into evenly numbered buckets. What does that mean? Well, what I'm doing is I'm taking quantiles of this entire distribution, and I'm going to make it so that each bucket that I'm deciding, or each bin I'm deciding, has the same number of records per bin. The point of that is just so that I could predict more easily overall, and that's because, as you can see, this is a log normal distribution, and sometimes it's difficult to predict based off of just simply NLP tasks. Sometimes it's just difficult to predict the actual values from a regression point of view. And so we're going to use classification because it's a little bit easier for us to evaluate certain cases, and we actually can talk about things maybe a little more intelligently when we're comparing the results. And so we're just doing classification here. It's quick, short, easy example. All right, now the different ML techniques. So as I discussed before, there's a few things that we have to kind of keep in mind when we're doing our overall training, such as normalizing the data, such as making sure that the text has a decent representation. So we're going to dive into each of those. So first is textual embeddings. So textual embeddings are needed for any NLP task. So they normally come in the form of these two. They either come in the form of a term frequency, inverse document frequency embedding or transformation, or what's called BERT. So a BERT embedding, so I'm going to tackle that first, is the reference towards the transfer learning. So there's a model called the BERT model that has been trained by Google. I'm taking that model that was used for a very specific NLP task, and then taking the embeddings that was received, that feature map that was learned through that training process, and then using that onto my data. And we're going to see some very interesting benefits from using BERT over this other embedding transformation. So I'm going to go back to the first point here. Now, this is a term frequency inverse document frequency transformation. So this right here, it's very interesting. So this relies on the vocabulary of the data that you feed it initially. And then it uses that same vocabulary to then go and try to create a different representation of new data. So term frequency inverse document frequency, essentially, if you think about it, is the term frequency. So the number of times a term shows up in a single document divided by, or times rather, the inverse document frequency, which depending on the equation to use, sklearn has a different implementation. But essentially, what this sometimes is just the log of the number of documents divided by the number of documents a term shows up in. And it's the log of that ratio plus 1. So that is the textbook definition. sklearn, they add 1 in both the numerator and denominator of that ratio I just mentioned. And that's the the main difference there. But it's very interesting, and there's a lot of pros sometimes to using this particular type of vectorization, type of embeddings. But there's also some cons too. So let me discuss that right now. So the pro of using term frequency inverse document frequency, or also called TFIDF, is it's quick, easy, explainable. That's it. That's pretty much the main driver. The con is that it's very difficult to generalize across another data set has a different corpus, different vocabulary. So an example of that is the sentence, the chicken is brown. That's a sentence, right? But then you have the hen is brown. Depending on where that actually sits in the training and test split, let's say, for example, in the training split, you have the chicken is brown. It's going to see the chicken is brown. It's going to see each of those words, going to be able to create the actual TFIDF value for each of those words in that document. But then once it sees the hen is brown, even if it's the same understanding in English, because of the fact that it's a completely different word, it's not going to be able to capture that. So the vector form could be like, say the chicken is brown, be 1, 1, 1, 1. It's going to be different in comparison to now the hen is brown, which may be 1, 0, 1, 1. And depending on your learning tasks and depending on how things are kind of learned, that 1, 0, 1, 1 could lead to a very different result in comparison to that 1, 1, 1. And so that's a huge con in TFIDF. The other con is keeping sequences in mind. So for example, the chicken is brown is a sequence of words. So you might create, say, a single vector for essentially each column represents whether it's one of the words, the chicken is brown. And so you'll have something very similar. So 1, 1, 1, 1 in one row with 4 columns. It's going to be 1, 0, 0, 0 for one sequence slice. And then the second sequence slice is 0, 1, 0, 0. And then you have 0, 0, 1, 0, and then 0, 0, 0, 1. And this is to represent that the first slice is going to represent the word the, and the now 1 corresponds to which part of the sequence did this word show up. And so that is a normal data distribution that you can use, a data structure you can use for deep learning. However, TFIDF can't capture sequences. The best it can do is do something called bigrams or trigrams, where you try to catch catchphrases. So maybe look at the chicken and you say, okay, this is one, and then you have is brown, and maybe that's another catchphrase. And so it tries to capture things, and that's a bigrams example. And sometimes you can capture some nonlinearities with bigrams, but there's a lot of research that shows that sometimes it's not sufficient, and bigrams itself produce a lot of sparsity because not all combinations of words is is a phrase or a phrase, and so there's a lot of gaps sometimes when it comes to that, and so and when it comes back to the hen, again, the phrase the hen doesn't then relate to the chicken, and so therefore it's completely miss out the entire TFIDF factorization scheme. And so that's a big con, and so there's a lot of cons when it comes from a validation standpoint. BERT, on the other hand, the only con from BERT is actually that BERT in and of itself can't be fully or fine-tuned unless you're embedding it into a deep learning network. So we have a few methods here that we use. We do have a deep learning network that we have used for this example, but the other models that we use actually cannot fine-tune the BERT model. Meanwhile, we can fine-tune the TFIDF factorization across all models. We can't do the same for BERT. But we're going to see that BERT is more advantageous and allows us with more flexibility. But that's something that is a con, or at least a caveat. All right, so next is dimensionality reduction. So this is really only applicable for certain models. So for example, and for certain data. So for example, let's say you have a large feature space, right? That TF-IDF factorization. Maybe you have millions of words in your corpus. So you're going to have a million long matrix. Number of columns is going to be 1,000,000. And let's say the number of rows you have is 1,000, but you still have 1,000 by 1,000,000, and even though it's very sparse, it's still large. When you're throwing that into a model, it's sometimes very difficult for the model to properly learn on top of that information because it's just so big and so large. So what do? We want to reduce the dimensions. And so we actually use truncated singular value decomposition, or truncated SVD. Now, truncated SVD is a very mathematical, way of handling things. But think of it like this: if you're familiar with eigenvectors, or maybe you aren't, or maybe you should because it's something that was mentioned in high school at some point, you'll actually see the equation for SVD broken down in a very nice way. So let's say you have a matrix A, and it's going to equal a matrix U times a matrix, say, D times matrix V, and add a transpose. And if you don't know what transpose is, then you should Google that. That's typically the SVD breakdown. Now, if you were to try to solve the equation, it's going to be difficult because you have a U matrix, you have a V matrix, you have a D matrix. How do you break it down? How do you solve it? Take the transpose of that. Then you have what? Transpose of A equals now V transpose of D, and then transpose of U. And let's assume D is a diagonal matrix, meaning that D equals D transpose. So you have A equaling, again, U, D, V transpose, and A transpose equals V, D, U transpose. Another single value decomposition. Start multiplying A and A transpose and swap that with A transpose A, and you actually get now that those two matrices, which are always proven to be square, actually now represents a eigenvalue decomposition, with now the U and the V matrices representing the eigenvalue or the eigenvectors, depending, of course, on how you multiply that A and A transpose matrix. So that's a highly mathematical explanation of things, but this is actually very useful and typically a method that's used to help simplify the feature space for a term TFIDF vector. And that's typically the route that's taken. Now, when it comes to, again, back to performance, sometimes it helps from a runtime performance standpoint. Sometimes, again, it simplifies large feature space. And sometimes it makes regularization easier. So what do I mean by that? Well, again, if you have millions of terms, that means you can have millions of coefficients for a linear model. And that's a baseline example. How do you then regularize each of those? It's more difficult. And we'll talk about regularization in a few moments, so please bear with me. But how do you manage that? It's, again, very difficult. And depending on the type of model you use, it gets even more and more complicated. So dimensionality reduction is used, but it's really only used a couple cases. I've used it within a couple linear examples that I'm going to talk about in the techniques section. I also did use it a little bit in the one example of extreme gradient boosting. Actually, both examples of extreme gradient boosting, and that's just, again, simplify cases. And again, I'll talk about that in the next slide, in the next slides with the techniques. Now, standardization's there. It's very simple. You're just essentially assuring that all your data is on the same scale. Now, TFIDF, your data is on the same scale no matter what, anyway. And similarly, with the BERT embeddings, they're on a similar scale too. So it's not as if they're not on the same scale. But what this does is it helps me ensure that the data, again, is definitely on the same scale. And it helps a little bit with the regularization of the models. Again, this is the aid to regularization. Well, again, we'll talk about next. So model regularization aims to restrict scaling of some feature importances of the weights of your model, or it can be used to eliminate feature importances. Now, why would you use regularization? Well, the answer is in point 3. You are seeking to prevent overfitting. Overfitting is a common problem within data science, within machine learning. It just means that your data is learning way too much from the training and not generalizing enough. So how do you do that? Well, you regularize by sometimes actually affecting the overall feature importances directly. There's other methods too, such as randomizing, data, augmenting data. There's ways of doing regularization, but the common is just to add restrictions on top of your feature importances, and that's the most common. Bayesian hyperparameter tuning. So this is used to train the model parameters of the model architecture that's chosen for our process here. Now this is a little bit different from model optimization. So model optimization really refers to sometimes the lower level aspects of the model, such as gradient boosting, choosing the right, say, learning rate, which sometimes can be linked to directly towards the actual model training. There's sometimes some processes that optimizes the learning rate based off the gradient, and there's a lot of things in particular that, truth be told, helps with the model process. However, it's really just simply a lot of times just the algorithm in play. So hyperparameter tuning optimizes or chooses the best parameters that optimizes the architecture and a given metric. And so that is essentially the entire premise of Bayesian comes into play, because there's really 3 different main forms of hyperparameter tuning. There is a grid search, which exhaustively looks across the entire space of parameters, which may not be a lot if you're just optimizing against maybe 2 or 1 parameter, but it may actually be, a 20 by 20 matrix. That could be a lot, and depending on, of course, how long it takes to train the model, it may be a long training process. So grid search, while may be effective in small parameter space cases, the moment it gets larger, the moment it really becomes more advantageous to really consider not grid search, but another method. There's another one called randomized hyperparameter tuning, which essentially just means that you take that space that you have, and you just randomly sample, and you just keep randomly sampling and choose the minimum of that. And that's fine. It's still not the most optimal solution. It might be better than maybe your default parameter solution, but it may not be the optimal one. And then you have Bayesian hyperparameter tuning. Now, Bayesian hyperparameter tuning, what it does is it first randomly samples just to get an initial understanding of the feature space, rather the parameter space and how it relates to your metric. But then it starts using Gaussian regression, process regression, where it learns how the parameters correlate now or relate to the metric you're trying to optimize. And then once it learns those parameters, it seeks to then look for some type of space where it sees there's room for improvement. And so it optimizes on that. And then it becomes a different optimization scheme. So Bayesian takes use of the first the what's predicted. It also makes use of the initial distribution of your parameters. So let's say you said some parameters are integer based, uniformly distributed, real numbers uniformly distributed. You can even state that some are real numbers that are log distributed. Then what happens, or log uniformly distributed? Then what happens is it starts assuming based off of those prior information of your parameters and looks to see the posterior, aka the predictions that were made and the metrics that were then created. It's able to then relate those priors to the posterior and then able to use Bayesian statistics to kind of randomly walk through these parameter space in a way that really gets to the actual sometimes root or really close to the actual minimum of your function. So we're using Bayesian hyperparameter tuning for about 3 models. I didn't use it for 2 for 2 different reasons actually. One, it was actually due to some type of weird metric calculation. Something was a 0, then turned to infinity, and so we're keeping it simple for that one. No parameter tuning there. And the other one is a deep learning model, which the package I use particularly for this use case wouldn't necessarily work for wouldn't just work. There's other packages there to do hyperparameter tuning, Bayesian hyperparameter tuning with a deep learning network on the parameters of the deep learning network, but we're not doing it here. Now, the different model architectures. So first, we're going to start off with the TFIDF vectorization with logistic regression with what's called an elastic penalty. So you get your textual information, you transform into TF-IDF vectors. Then you do truncated SVD, truncated singular value decomposition. And then you're going to link that now to standardization, standardizing now your components to make sure that everything is on a similar scale. And then you do logistic regression. Now, logistic regression here is used to predict the likelihood that you are in a bucket. Now, the elastic net penalty relates to that model regularization I was talking about before. So what is that? So there's 3 different types of regularization when it comes towards weight regularization. And you can make this even more complicated, but there's normally just 3 specific types of penalties. You have your L1, L2, and elastic. L1 basically states that and there's 2 definitions for this, so I'm going to use the geometric one because it's a little bit easier to describe. Basically, the sum of the absolute value of the weights of your linear model must not exceed a particular threshold. The other definition, for those who are curious, is you're minimizing not just the initial loss function for logistic regression, which is the the regular cross entropy log loss function, but you're also minimizing a scalar times the sum of the absolute value of your weights. So that's the L1 regularization. L2 is similar, except you're doing the squares. So you're doing the sum of squares. So in this particular case, sum of squares, the coefficients have to be no more than, say, a particular threshold, or you can throw in inside your loss function definition, and you try to minimize that, sum of squares times some type of, coefficient. ElasticNet is actually the linear combination or weight combination of the L1 and L2. And so that's the actual definition between these two functions. Definition of all these regularizations, which are also functions. Now, the interesting thing is this. L1 allows your coefficients to go to 0 almost immediately, almost very easily. L2 restricts just the scale of those coefficients. And then elastic is the combination, right? So not only it restricts sometimes the scaling, but also sends some to 0 if applicable, if it makes sense. So that's the elastic net penalty. So we're going to use this across pretty much our linear models, for our use case here. Now we also have TFIDF factorization with XGBoost regression. I call it regression because this logistic regression is a linear regression. You're training essentially for probabilities. That's the actual output in logistic regression. In classification problems, you just do kind of like what's called a hard sigmoid type function, where essentially you just clip the values at a particular threshold, normally 0.5. So sigmoids predict between 0 and 1. That's the probability, or represents a probability. And then essentially you just clip that value. Now it's, again, very interesting to use XGBoost in this scenario here, because XGBoost, what it does is it actually uses decision trees, which, if you don't know what that is, you can Google it. Quick description is giant glorified if-else statements. But these if-else statements optimize something in such a way where the prediction relates to how the if-else statement splits your data, right? And then add that on top of multiple other types of decision trees that are used in a way that minimizes and optimizes for your loss function. So we're using XGBoost here, which is called extreme gradient, so extreme gradient boosting. Now we're also doing BERT embeddings as well. Again, very similar to the TFIDF, and then this is for the elastic net, and this is the comparison between TFIDF and BERT, right? So this right here gets your textual embeddings, brings it to your truncated SVD, brings it to your standardization, then brings it to your logistic regression. Same exact architecture, you're just swapping out the embedding space. And then, again, very similar for the XGBoost. Now, for the deep learning network, it's a little different. So for the previous, 4 models I talked about, my architectures, you're taking strings and mapping it to a 2-dimensional space. That's what we're doing there. We're taking and mapping it to 2-dimensional space. Here, what we're doing is we're taking a string and mapping it to a 3-dimensional space, when that 3-dimensional space is in the form of a sequence of 2D vectors, or as I described earlier with my example, where you had the chicken is brown, where you have the chicken is brown, 1 0 0 0 1 0 0 0 0 1 0 0 0 1, like that particular breakdown. That's taking its text and transforming to that type of sequence, then feeding it what's called a long-term short-term memory model, LSTM model. And the goal of this is to use the previous step and the features you learned from the previous step to then help you with the next step. And so it's sequential. So it takes the entire process and goes forward and tries to remember a little bit of the past until you create a new feature map or feature space, and that gets used. In this particular model, I'm using what's called bidirection. So what it does is it goes forward and does that, and then it looks backwards, right? So it goes forward and backwards, and then returns the final output. It goes forwards and backwards, and I go forward one more time, and then returns the output. Then I standardize that output using batch normalization within the TensorFlow mindset. And that actually is really just standardization. You're centering your values, making sure that that the standard deviation variances are no more than 1, so you really have that. And they have what you call your fully connected layer, which in this particular case, it just means that we're taking the final output, that normalized values, bring it down to a another fold space, another smaller space. For this particular case, we're predicting the probabilities for each class, whether you're in a particular bucket across all the buckets. And then essentially, I make sure I use what's called a softmax function, which basically normalizes the probabilities of anything ever happening, so then that the sum of the probabilities across a singular row across all the columns equals 1. And so this is just enforcing a categorical way of looking at things, something that's already done intrinsically in the other models I mentioned, XGBoost and Logistic Regression, but I want to be sure I mention that here because some people do things a little differently. Now let's look at these results. So this is a TFIDF, vectorization with logistic regression, and we kind of see here something a little bit interesting, right? So note that the model does actually pretty well with values that are exceed, say, a particular threshold within the initial, bucket for the number of claps an arc received. And just for information, the left side represents the true, and the bottom side represents the essentially the predicted, and that's kind of that breakdown there. So the model predicts very well on the higher values, but as you get a little bit closer towards the end, you see that it kind of struggles a little bit. See, it's a little all over the place. Some of these values are very low. Some of them are never predicted correctly. For example, that 25 to, for example, this one right here, 7 to 20. 7 to 20 is never predicted at all. Like, it's just not. And similarly also with the 58 to 157, it's never predicted well. So like those are two cases where it just didn't do well. And some of this data is probably outliers, and so some of this is a little off. You're going to see that a little bit more so as we get more complicated examples. But as you can see here, it's again a little scattered, but it does kind of well in some cases, but it could do better. Now this is a little different. This is TFIDF with XGBoost, and you can see now very different examples. See? It changes a lot here. Where some of this becomes less, so you see there's less a little bit up here, so it doesn't say underpredict significantly. But some of these values are pretty, and some of these values are getting higher. For example, it's able to predict this 1 and 2 very, very well, which in the past it wasn't able to, but now it is. But as you can see, it's a little bit more spread out, but it's not as bad as maybe we could expect, and we'll see that in the plot. I mean, in the comparison of the scores that we received. And then we have the BERT and logistic regression. So this is again a little interesting. So note here, so this is BERT logistic. If I go back, and this is TFIDF and logistic. So note here, we're missing some values, right? Or rather, these misclassified values aren't really there. We have some here, but we're doing better. And remember that 720 we didn't predict at all? We're starting to predict that. See there. Now we are still missing the 58 to 157, like that's still missing. And in the XGBoost example, we got it here, but we're missing it here. But we're doing better. And you can see that we're doing better. You can see that. Now, here we have BERT and XGBoost. Here, and we lose the 7 to 20, but we gain the 58 to 157. And as you see, again, that this is not always going to be always filled out, but this does a pretty good job. Then we have the deep learning model, which, it's there. It does what it needs to do. It's pretty interesting. It's able to predict a 7 to 20 at least to some level of degree. It misses the 558 to 157. And it also misses 511 to 935. But it does a pretty good job still. Overall, this is what the cross-validations look like. So during the process, I'm using what's called the F1 score. And the F1 score is used because it helps us keep track of the true positives and the true negatives and the false negatives and the false positives, and making sure that we're capturing the true predictions. Because it's very easy to over-predict and predict all ones, depending, of course, on your distribution of your data, or all zeros, depending on the distribution of your data. Well, in this particular case, I'm just making sure that I'm predicting the true positives correctly, while minimizing the false positives, which is precision. And recall is predicting the true positives and also minimizing the false negatives. It's kind of like that breakdown right there. F1 score is a combination of those two. And so this is the breakdown here. Higher is better. And as you can see with the BERT elastic net, which I showed you before, it performed actually pretty well. You can see that it actually did pretty well. If you look right next to it, which is TFIDF elastic net F1 micro, you see that that actually doesn't do well. You can see that the score barely reaches over 0.5, and that's for the maximum. That's the maximum score. So it doesn't do pretty well. And that's pretty sad, but that's something I kind of expected given the cons I described earlier. Now, BERT in general has done well. You can see that also with XGBoost. You look at ElasticNet and do those comparisons to the TFIDF versions of that, and you see that the model actually hasn't done well overall in comparison to their siblings. Now, XGBoost does say, perform a little bit better than the ElasticNet, and that's especially true with TFIDF XGB. Even though I didn't do any hyperparameter tuning with that, that still outperformed the TFIDF ElasticNet. So, which means the nonlinearity that was caught was actually able to be used in the TFIDF vectorization. The BERT model for XGBoost actually, it does at one point perform better than the ElasticNet, but if you look at the average, on average, XGBoost does okay. It's like, the F1 score is not phenomenal, but it does good enough. But then the ElasticNet doesn't perform, it performs better. And so the overall average of these values are a little bit higher, even if the maximum is received higher for the BERT XGBoost. The BERT ElasticNet performs on average a little bit better. The one thing in particular that's kind of interesting to note is actually the BERT deep learning model. Now, there's a lot of caveats here with this model and some things that I didn't do because it's a little bit more difficult to do this in this particular experiment. But BERT deep learning actually does just as well as the ElasticNet. There's a few things I didn't do here. One, I didn't do any regularization on any of the parameters in this deep learning network. There's none. Outside of batch normalization, which is standardizing the data, I didn't do anything to regularize the coefficients inside of the data. I did none. Two, I didn't do any form of early stopping, which kind of happens within the ElasticNet and XGBoost. With XGBoost, the learning rate affects the overall scaling of your data, and I'm also optimizing for the number of decision trees to be used, which kind of helps with early stopping, make sure data isn't overtraining. So I do that there, but I don't do that with the BERT model, BERT deep learning model. So those are the two major differences there. Now, even though this model, say, doesn't perform maybe as well, say, as the other four, just remember this. BERT does not or cannot be fine-tuned unless it's injected into a deep learning model. So transfer learning is interesting because you can do two things. You can do just feature extraction, feature maps, but you also can fine-tune your feature maps relative to your new learning task. So can't do that with XGBoost, can't do that with ElasticNet, at least exactly. There's things you can do to mirror ElasticNet with XGBoost. You can, within deep learning, you can. You just change your, not ElasticNet, but your logistic. This is representing the penalty, but this is the logistic regression with the ElasticNet penalty. But there's ways to mirror things a little bit between deep learning and what's normally an sklearn, just by changing the model, so to speak, and using the same type of inputs. But you gain more for your buck just by using the sequence to sequence, which isn't fully optimized here, firstly, and also secondly, there's no regularization at all. So that's something to keep in mind, even though this clearly, of course, doesn't perform at the same level and degree. Here are my references. Please check them out. This is all, sklearn, TensorFlow. This is the optimization package I use as Scikit Optimize. You can refer to this. It's really helpful and useful. And thank you, everyone.